We're now going to talk about modifying functions. And we're going to talk first about combining functions. And similar to numbers, we can combine functions. We can add, subtract, multiply, and divide functions. And there's special notation we use when representing each of these operators. F plus g of x is f of x plus g of x. So if we're talking about the function itself, we say the function f plus g. And this is its own function. And now we can create a function by subtracting two functions. And this subtraction is f minus g. We can multiply fg of f, and we talk about the function fg, and we can divide our functions, and f over g is the function f of g x divided by g of x. Now, when we combine functions in this way, the natural domain is impacted. Now, when the natural domain of two functions that we add together, when we add two functions together, what we do is we take the intersection of our two natural domains. And this subscript means the domain of f and the domain of g. And when we subtract, we also take the intersection of the domains. When we multiply, we take the intersection of the domains. But when we divide, it's slightly more complicated. We do intersect the domains, but we have to add one more constraint. We add the fact that g of x does not equal 0. So we add in the constraint that we're not dividing by 0. Now, if f and g are functions, there's one more way in which we can combine them, and that's composing them together, applying one function followed by the next function. The composition of f and g is denoted f of g, the little circle. That little circle is f of g of x, meaning we first apply g, then we apply f. Now we talk about the function f of g. Now the domain of f of g is a little bit more complicated. So the domain of f and g, f of g, is equal to the set x that's in the domain of g. So we start with the domain of g, and we add the constraint that g of x is in the domain f. And this, calculating the natural domain of f of g, is sometimes harder. So a question that I have, or is often asked, is if f of x equals x squared and g of x equals root x, are the compositions f of g and g of f the same? And to talk about this, we're going to show that they're not quite the same, and we're going to use the natural domains to do so. So if we look at f of g of x, this equals f of g of x, which equals x root x all squared, which equals x. And if we look at g of f of x, this equals g of f of x, which equals the square root of x squared, which equals x. Now these look like the same, but what are our domains? Our domain of f is the set of x in the real numbers. And our domain of g is x in the real numbers such that x is greater than or equal to 0 because of the square root function. Now let's look at the domain of f of g. Well, this is going to equal the set of x in the domain of g such that g of x is in the domain of f. Now we're going to expand this a little bit. So this is x greater than 0 such that such that square root x is a real number. Well, this is true for all x greater than or equal to 0. Thus, the domain is domain f of g equals the set x greater than or equal to 0. That's our domain. But the domain g of f equals the set x in domain of f such that f of x is in the domain of g. Well, what is this? This is the set x such that x squared is greater than or equal to 0. This is true for all x in the real numbers. Thus, the domain of g of f is equal to the set x in the reals. So adding this, we get the domain of f of g is equal to the set x greater than or equal to 0, whereas the domain g of f equals the set of x in the real numbers. And let's adjust this to get our proper set builder notation. X in the real such that x is greater than or equal to 0, whereas here we have the set x greater than 0. And we can see as the natural domains are different, the functions are different, which is very interesting. And here, one of the things I always say is it's best to just practice. So here, what I'd like you guys to do is go through and do all your compositions and figure out what your domains are for all your compositions. And here we can add one last composition of g divided by f and see what their respective function and the domain of those functions. And you can also do g minus f. This will give you a lot of practice on determining your domain constraints of composed functions, as well as practicing composing your function. Next, we're going to talk about the properties of functions. Now, the first property we're going to introduce is odd and even functions. Now, a function is odd if f of minus x equals minus f. And a function is even if f of minus x equals f of x. Now, odd and even functions are forms of symmetry. An odd function has rotational symmetry about the origin. And an even function has reflexive symmetry. Now, what is rotational symmetry? Rotational symmetry is if I take this curve, and if I select that curve, so if I take this curve, I select that curve, I copy it, paste it, I rotate it around, all the way around, and I paste it there. That is oh, not quite. It's not quite rotated properly. I got to move it down a little bit. There. It's not perfect, but you guys get, oh, let's see if we can rotate it to make it a little bit better. And then down That's better. This would be an odd function. It's rotationally symmetric. Now, an even function has reflective symmetry about the x-axis. So if I take the function and I take its mirror image about the x-axis, that is a even function. Now, to determine if a function's even or odd, we complete the following steps. We start with f of minus x. We plug in x minus x wherever you see an x. We simplify the expression, and if you get f of minus x, it's odd, and f of x, it's even. So let's take a look at a couple of examples. So if I look at f of minus x, this equals minus x squared minus 2 over minus x, which equals x minus 2 over minus, or x squared minus 2 over minus x, which equals minus x squared over minus 2 over x, which equals minus f x. Therefore, f of x is odd. Now, here we've shown the function is odd. We plugged in minus x, we simplified our signs, and we got that equaled minus f of x. What about showing a function is not even or odd? Well, what we have to do is we have to come up with two values. One value where f of minus x doesn't equal f of x, and one value where f of minus x doesn't equal minus f. So here, what I'm going to do is I'm going to look at f of minus 1. And f of minus 1 equals minus 1 plus 1, which equals 0. And f of 1 equals 1 plus 1, which equals 2. Well, here, f of minus 1 does not equal, which equals 0, does not equal minus f of 1, which equals 2, minus 2. And f of minus 1, which equals 0, does not equal f of 1, which equals 2. Therefore, it is neither even nor odd. And as practice, I highly encourage you to work through these functions. Determine whether or not they're even or odd or neither. And as extra practice, use the definition of even and odd functions to prove each of these properties hold. And I'm going to go through this example for you. F of minus x equals f of x, and g of minus x equals g of x. Well, f over g of x equals of minus x. Let's erase. F divided by g of minus x equals f of minus x over g of minus x equals, using our definition here, f of x over g of x, which equals f over g x. Therefore, the function is even.